Hi gang, so as we get back to work here, we're going to keep working with complex numbers. And in this section what we want to do is see how the complex numbers are represented on the complex plane, which we've already talked about a little bit, and different ways to represent complex numbers. So let's roll. So first of all, as we already worked with in class a little bit, the complex plane is a lot like the Cartesian plane, where you have what would have been the x-axis, that's now our axis for the real numbers, and the y-axis is the imaginary axis. So any complex number has some real and imaginary component to it. So for example, 8 plus 5j, that's going to be a complex number with a real part of 8 and an imaginary part of 5. So 8 to the right and 5 up. That is the imaginary number represented on a complex plane. And again, that's really just a vector. You've done vector work. You did that in Tech Math 1 A and B. It's the exact same idea. The number 6, that's got a real part of 6 and, if you will, an imaginary part of 0. And so, real part is 6, imaginary part is 0. And our last one, negative 2j, that's got a real part of 0 and an imaginary part of negative 2. So can you picture where that complex vector is going to point? I'm sure you can. It's going to point straight down 2 units. So you can probably guess then that we can do all the same thing with vectors that we can do all the same thing with complex numbers that we can do with vectors. So let's review a few things about vectors, and that's going to help us build some more facts about complex numbers. So you can add and subtract complex numbers pretty easily. First of all, you can add complex numbers by adding their real parts, and in this case negative 2 plus 9 gives us a real part of 7. Negative 6j minus 3j gives us an imaginary part of negative 9j, and that is the total of those two complex numbers. Now, you can also add them tip to tail as if they were vectors. So negative 2 minus 6j, that vector is going to be right down about here. 2 to the left and 6 down. And 9 minus 3j, that's going to be 9 to the right and down 3, right about there. And we can add those vectors tip to tail, which means we can grab either vector and move it to the tip of the other. So if I grab that red vector and move it down here, that's called a translation. I'm just translating that vector over to its new position. And of course it kind of leaves its old position at that point. Then our resultant vector should be from the beginning of the first complex number down to the tip of the second. So the beginning, from the origin down to the tip of our ending point. And if you make a note of where that ending point is, the location there is 7 for a real part and negative 9 for an imaginary part. So we would have 7 minus 9j. And of course that corresponds to what we said it should be. Let's do one more. Let's take a look at a subtraction. Now, what that means for us is that we would distribute that negative sign across both parts of our second imaginary number. So that's going to be negative 2 minus 9, or negative 11 for our real part. Negative 6, that's going to become plus 3. So minus 3j for our imaginary part. If we view that from a tip-to-tail addition perspective, our first vector, the blue one, negative 2 minus 6j, is going to be about the same as it was in the previous example. Our second vector, 9 minus 3, that's going to be about the same. But since we're subtracting, you may or may not remember this from our earlier work with vectors, but if we translate that vector down here, it lands right there just like in the previous example. But if we subtract it, that's not the vector we want. If we subtract it, we want to point in the exact opposite direction. If we're subtracting the vector, we should point it in the other direction. And so this vector disappears, and our resultant then is the blue vector minus the red one, or plus the opposite of the red one, and that's our resultant vector right there. And if you take the location of the tip of that vector, it's at negative 11 and negative 3 in the imaginary direction. So negative 11 minus 3j, which is again exactly what we were expecting. Okay, that stuff is pretty easy. Now let's look at another property or characteristic of vectors that's more useful to us. Let's take a look at these three vectors again, 8 plus 5j. We're going to write these in polar form. Remember, polar form of a vector gives its magnitude and its direction relative to standard position. So 8 plus 5j, as we saw earlier, is going to be about right there. So let's start by figuring out what our magnitude is. You might remember from our earlier work that the radius or the magnitude of that vector is found by applying the Pythagorean theorem to that vector, where the imaginary component is 5 and the real part is 8. So we can say that our radius would be, or our magnitude would be the square root of 8 squared plus 5 squared. And if you compute that, you end up with about the square root of 89. And in fact, you can generalize that and say that our magnitude can always be found by taking the square root of our real part squared plus our imaginary part squared. That's particularly useful. Let's keep that. Now, if we want to find the direction of that vector, our angle theta down here, we'll use the tangent function. And you probably remember, or at least could recognize, that the tangent of our angle theta in this case would be opposite over adjacent, which is 5 over 8. Apply the inverse tangent, and I think you would find that theta is equal to about 32.0 degrees. Now again, to generalize that though, we could say that in general the tangent of the direction is equal to our imaginary component, which in this case was 5, but in general is your b value, divided by your real component, which for us was 8, but in general would be your a value. And so the tangent of our direction will be b over a. Let's keep that generalization in mind. But to finish up our initial question, to write 8 plus 5j in polar form, we've done it. That is equal to the square root of 89 at a direction of 32.0 degrees. If you wanted to round that off, we could say 9.434 in a direction of 32.0 degrees. Now the other two examples I have here are a little bit easier. Let's figure out what 6 is in polar form. Well, the vector 6, real part 6, imaginary part 0, as we saw earlier, that's going to lie right there. Now we already know what that's going to be. The magnitude of that vector is 6, and its direction is 0 degrees, so there's really no work to do to put that in polar form. And negative 2j, as we saw earlier, that is down 2 units. Clearly that vector has a magnitude of 2 at a direction of 270 degrees. And we've got that one written in polar form. So let's summarize that. In general, when you want to convert a vector from complex form, this is what we call complex form, if that's not been made abundantly clear. And we want to convert that to polar form, which is shown in red there. Then these are the two relationships you need. Your magnitude is the square root of your real part squared plus your imaginary part squared. And your angle is the inverse tangent of b over a, which is related to the results we showed a minute ago. So I want you to take just a minute here, and I would like you to convert negative 6 minus 7j, turn that into polar form. You can pause the video and resume when you're ready to see the solution. Okay, this vector is got a real part of negative 6 In an imaginary part of -7, this vector is pointing down here into quadrant 3. So based on these two relationships, we can say that the magnitude of this vector is going to be the square root of the real part squared plus the imaginary part squared, which becomes the square root of 85. So that's the magnitude of our vector. To find our angle, we know that the angle theta is going to be the arctan of our imaginary component, which is -7 over -6. You can type that into your calculator. Your calculator will lie to you a little bit here. Your calculator is probably going to tell you that's 49.4 degrees. But clearly 49.4 would be in quadrant 1. We're not in quadrant 1. We need to add 180 degrees to that to get us down into quadrant 3. This angle is 229.4 degrees. And so we've converted our vector into polar form. It's going to be the square root of 85, which is about 9.220, at a direction of 229.4 degrees. Done. Okay, let's go the other direction. Let's take a complex number in polar form and convert it back into complex form, or what we sometimes call rectangular form also. So let's take 16.5 at 107 degrees. Should be able to picture that vector. 107 degrees is going to be somewhere up here. We don't know exactly where that's going to be, but it's safe to say that it's going to be in the second quadrant. And we know our magnitude here is 16.5. So to figure out what the real part is, we need to figure out what our A value is. Since our magnitude is represented by R, we could certainly say, based on our angle, that the cosine of our angle is the adjacent side, which is A, over our hypotenuse, which is R. And a little bit of rearranging, multiply both sides by R, and we can see that R times the cosine of theta is going to be our A value. And so that's the first of our two relationships here. To find the real part, we just take the magnitude times the cosine of our direction. In our case, that means that our A value is 16.5 times the cosine of 107 degrees. And if you do that, you'll end up with -4.82, which approximately agrees with our sketch here, about 5 units to the left. And by all the same logic, if we want to find out what our imaginary part is, we need to figure out what the opposite side of that triangle is, or what our B value is. Here we could say that the sine of our angle has to be the opposite over hypotenuse, or B over R, multiply both sides by R, and R times the sine of our angle theta is equal to our B value, and that's our second relationship. Now in our case, that's 16.5 times the sine of 107 degrees, and that turns out to be about 15.78. which again is approximately consistent with our picture, about 15 or 16 units up. So to convert this into rectangular form, we can conclude that 16.5 at 107 degrees is about the same as -4.82 for our real part plus 15.78 J. And there we go. Now this raises kind of an interesting question. Let's find out what the complex conjugate of 6.7 at 59 degrees is. Remember, if we have a complex conjugate that is A plus B times I or J, then the complex conjugate is A minus B times J. So for example, if we had the complex number 11 minus 6J, then the complex conjugate has to be 11 plus 6J. Conjugates are useful for doing complex number division, among other things. So the question is, what is the complex conjugate of 6.7 at 59 degrees? Well, we could turn this into rectangular form and switch the sign on the imaginary part, but there's a simpler approach. Let's think about this kind of intuitively here. If you think about the complex plane, 6.7 at 59 degrees would probably be somewhere up here in quadrant 1. Now the conjugate has to have the same real part, that is to say it still needs to move us to the right by about the same amount. Our A value has to be the same. But the imaginary part, the B value, is what gets reversed. So the complex conjugate should be A units to the right and in the opposite direction of B. So our conjugate will be down, and the imaginary component will be negative B. So we don't know what the conjugate is, but we do know it has to look like that. But if it has the same real part and the opposite imaginary part, then that means that the short way to say that is, instead of a vector that points up, it's just going to point down. And if the vector were to point down, it would point up. All that does is switch the imaginary part from top to bottom. And so that means that the complex conjugate still has to have the same magnitude, but what would its direction be? Well, instead of going up 59 degrees, we should go down 59 degrees. So the complex conjugate is 6.7 at negative 59 degrees. Now we could make that positive and call it 6.7 at 301 degrees, and we're done. There's really very little work to do there if you think about it in that way. And in fact, you can generalize that and say that in general, the complex conjugate of any number in polar form is going to be same magnitude at opposite angle. Okay, there's one more thing that we need to recognize here, and there's a third way to write a complex number. So we already know this form, which we call complex or rectangular. We're now familiar that we can also write this thing in polar form. But now we have another form called trigonometric form. And trigonometric form looks a little bit confusing, but it's going to have some big consequences as we move on to our next topic. Here's where trigonometric form comes from. Start out with the complex form of a number, or rectangular form, a plus j times b, or a plus bi if you prefer. Now we already showed in our earlier results today that the a, the real part, can be found by taking the magnitude times the cosine of theta. So we're going to swap that out and put it right there. We also showed that the imaginary part is r times the sine of theta. So we're going to put that in right here. Now that just tells us the magnitude. The j still has to be a factor on there to show us that that's the imaginary part. But after you do that, you'll notice that the complex number a plus j times b, or in other words, r times cosine theta plus j r sine theta, there's a common factor of r there. That can get factored out to the front, and that means that we can write a complex number in rectangular form as r times, not an angle like we did in polar form. Here we put the r out in front as well. But we can put the r out in front and say that that is cosine of our angle plus j times sine of our angle. Now again, that seems a little convoluted, but that's going to turn out to be useful for our operations here in the next 2 lessons. But in the meantime, let's just write this number negative 12 plus 6j. Let's write that in trigonometric form. So in other words, we need to make this take on that form. So we need to know the same 2 things as we would if we were going to polar form. We got to find our r value, and we got to find our angle. Okay, so we already know how to do that. Our r value is found by taking the square root of, from what we saw earlier, a squared plus b squared, and in this case r is the square root of negative 12 squared plus 6 squared. You can do the math on that, but it turns out to be the square root of 180. 13.42. Our angle theta is the inverse tangent of b over a, which in this case is the inverse tangent of 6 over negative 12. Noting that that's pointing to the left and up, it has to be in quadrant 2. That works out to be 153.4 degrees. You should verify that. Since we know our magnitude r, and since we know our angle theta, we can put this thing into trigonometric form. That means in trigonometric form this becomes 13.42 times the cosine of 153.4 degrees plus j times the sine of 153.4 degrees. And we're done. There it is. It's in trigonometric form. Boy, I gotta tell you, this stuff would be a lot more fun if we were all together working through it. I know that you all would have a lot of good questions to ask about this, but nonetheless, let's keep going. Okay, so here are a couple of examples of complex numbers in rectangular form, polar form, and trigonometric form, which is of course closely related to polar form. I've deliberately put a mistake up here, and I don't want you to use your calculator. I just want you to look over these three equivalencies, and in these 9 boxes, 3 rectangular form, 3 polar form, and 3 trigonometric form, I planted an error. You don't need your calculator to find this. I just want you to look at each value and see if you can find the mistake that's up here. Go ahead and pause the video, look this over and see if you can spot it. I'll reveal it and we'll discuss it in just a minute. Okay, for starters, let's look at the quadrant that each of these is located in. Our first one, negative 4.25 plus 7.36, that is definitely in quadrant 2. 120 degrees is in quadrant 2, and so that appears to be okay. You could pull out your calculator, which I told you didn't need to do, but you could verify that the magnitude of this vector is 8.5, which it is in both the polar and trigonometric form. All of these are okay. There's no mistake in any of that. If you were to check those conversions, everything would match up fine. The mistake is somewhere in the bottom 2. The second one, 109 real part, that moves us to the right, and down 50.7, that puts us down in quadrant 4. 335 degrees is in quadrant 4, and so 120 is our magnitude with a direction of 335. That matches the polar and trigonometric form. Everything looks good there. You could use the Pythagorean theorem to verify that 109 squared plus 50.7 squared, and take the square root gives you 120. You could verify the angle and you would find that all these are okay. The mistake is somewhere in the last one. Okay, let's look at the last one. Negative 16.8, negative 12.5 for imaginary. That means that we're to the left and down. That's in quadrant 3. But 216.7 is in quadrant 3, and that matches this. So where is the problem? Well, here it is. Look at the magnitude on this vector in polar form, 15.9. There's no way, and I mean no way, that a magnitude 15.9 vector can be 16 units to the left and 12.5 units down. The problem here, just by checking, if this vector is 16.8 units to the left, the magnitude has got to be at least 16.8. There's no way it can be 15.9. Think about that. You don't need your calculator for this, but our magnitude has to be bigger than 16.8. So the 15.9 here and the 15.9 here are okay. The direction of 216.7 matches this. These two are okay. But somewhere down here, we've got a miscalculation. It's probably this box right here. One of those numbers can't be right. So you could argue either this rectangular form of this number is wrong, or if this was right, then maybe these two magnitudes are both wrong. But hopefully you can see how you can, by glancing at these numbers, get a sense for about what they should be. Okay, that wraps up this topic. So you know how to convert numbers between trigonometric, polar, and rectangular or complex form. You know how to graph complex numbers on the complex plane. And you know how to add and subtract numbers on the complex plane. So I'll be giving you your assignment on Blackboard. Go ahead and proceed with that, and we'll continue this in our next topic.